I am Minghang from Peking University. I will present our work, Training Free Video Temporal Grounding using large-scale pre-trained models. This work was done in cooperation with Xinhao, Qingchao, Yuxin, and Yang. This work addressed the visual grounding task, which localizes the video segment most relevant to a given natural language query. As shown in the right figure, existing methods heavily depend on the training dataset distribution, leading to the performance drop under the old setting. Motivated by this, we aim to propose a training-free video temporal grounding approach that avoids reliance on specific datasets, improving generalization in real-world application. Recently, large-scale pre-trained models have shown strong generalization ability. This inspires us to transfer the ability in video temporal grounding, allowing baselines to enumerate proposals in the video and use the pre-trained vision language model to adjust the alignment between these proposals and the query, and select the proposal with the highest score. However, vision language models are often trained on images or trimmed videos. It can be challenging for them to understand the temporal boundaries of multiple events in untrimmed video. We also found that directly selecting the most relevant proposal ignores the dynamic transition while the action is being conducted. As shown in the figure, in the naive baseline, the model tends to ignore the beginning of the events. This is mainly because the vision language model is trained to associate the most discriminative visual cues with the corresponding text, rather than emphasizing the need to focus on dynamic transition and ensure the completeness of localized events. To address this problem, we proposed training-free video temporal grounding for the multiple events in the query. We prompt large language model to decompose the query into subqueries that containing single event and analyze the order and the relationship between subqueries. Then, we use the vision language model to localize each subquery and combine these results based on the input order and the relationship. For the dynamic transition, we explicitly model the dynamic transition and the static status after transition. A good proposal should begin with the dynamic part, exhibiting a notable increase in video text similarity, and followed by a static segment, characterized by a high video text similarity within the segment, while displaying a low similarity outside of it. Specifically, we first prompt the large language model to reason the query and provide the subqueries in time order, and the info the subqueries should occur simultaneously or sequentially. For the query, she sprays it with a spray bottle and continues brushing here. The large language model can analyze the query and decompose it into two subqueries by time order, and further infer the two subqueries should occur sequentially. Then, in the visual language model localizer, we calculate the cosine similarity of text and visual features using visual language model, and propose the dynamic score and static score based on the similarity. Dynamic scoring requires the similarity between the frames and the query should quickly increase, and static scoring requires the video within the event have high relevance to the query, and the videos outside of the event have low relevance to the query. The final scores is the sum of dynamic and static scores. Finally, we enumerate proposals in the video and select the top K proposals with the highest scores as candidates for each subquery. Firstly, we filter and integrate the localization results of all subqueries according to the order and the relationship from language model prompting. For the sequential events, they should follow the time order, and for the simultaneous events, they should overlap in time. Among the filtered candidates, we select the one with the highest total final score provided by the vision language model. We conduct experiments on the ActivityNet Captions and Schwartz standard datasets. We first compare with existing methods under the ID setting. Even without large language model, we have outperformed existing zero-shot methods, and with large language model reasoning and sub-events integration, we achieve zero-shot performance. We further compare the performance under the OOD setting. Our approach achieves best performance when the distribution of location and the text are changed, and even surpass some fully supervised methods. We also surpass fully supervised methods and achieve the best performance on the cross-dataset setting, demonstrate strong generalization ability. Here, we show some visualization of the outputs of large language model and the localization results of our methods. In conclusion, we propose a training-free video temporal grounding method that addresses the challenge of multiple events query and dynamic transitions between events, achieving the best zero-shot performance and demonstrate better generalization under the OOD setting. The project page and code are available by scanning the QR code. Thanks for your attention.